Okay, so I hope you could assist yesterday to the lecture with Marlon because today is about predicting process outcomes. So I think you yesterday you start with all the topic, and the idea is like today relate the code and the approach, right? So just before to start, some preliminaries you can see in this practice. Actually, this practice is gonna be more like a demo of the tool that we will use in Python, and but you have to play with this approach as well. So the idea is that you can check all the repository and at the end of this practice, because you will need to like perform some modifications in the approach, and that will be like your next homework. So the idea is like you can play with it. In this occasion, we will use Anaconda, and the links, let me share with you the links. We'll use Jupyter Notebook as well, but I'm not gonna share this time the notebook in Google Colab, because I'm calling some libraries that come from an approach, a different approach. So you need to install all the approach and all the environment and execute it in your local machine. So I'm just copy all the links in Slack so you can start downloading and installing everything that is needed. Oh, you can try to do it, but the thing is that I'm gonna use some external libraries. So if you want to use it in Google Colab, you need to download the previous repository, the repository that comes from the approach of Irene Teinema. And you need to upload that libraries into Colab and then start to call them. But the idea is that you actually need to use them in for your homework. So the idea that is better if you can start to use it in your local machine.
Which libraries are external?
Yeah, let me show you before.
Ah, okay.
So we have Anaconda here. The Jupyter notebook that we will use is in this link. So is this one. Ah, it's a little bit annoying. This is our repository for this practice. And we will use these libraries, the bucketers. We will use transformers, and this can have to be called externally. So if you want to use them, you need to upload them, all of them. Also the data. So it's a little bit more complicated to upload everything in there and start to call them than execute it in your local machine, right? So this notebook actually is based on this approach, the outcome-based predictive monitoring approach. You can find the repository in this link. But what happened with this approach is that is, of course, like from 2 or 3 years ago, and it's a little bit outdated in terms of libraries like pandas, for example. So what I did was like update that changes, so you can find the update in this other repository. So basically you have to focus in this one, in the second, in the adaptation. Probably in the future will be integrated in the main. I hope so. So let me check if you have access. Let me know if you have access to all the repositories. What libraries are we gonna use? NumPy, Pandas, Matplotlib, Seaborn, XGBoost, and scikit-learn in general, right? So until this moment, do you have any questions about the tools that we will use?
Maybe could you? I haven't used Bitbucket before. Could you show like where's the download button there, or should I clone the Git repository into
Ah, okay,
my own?
okay, yeah. Okay, you can access directly to the link I copied,
Yeah.
and then you come in here. Everything is over the window. And you have this button, clone, right? And then you have two options. You can clone directly to Visual Studio or clone using SourceTree, right? It's a Git repository. So as well, you can actually copy this and use this address and download it directly using Git.
All
But
right.
it's
Okay.
recommended
Thanks.
that you download the SourceTree application. It's this one. Looks like this. Okay. Okay. So now let's start with the topic. So as you know, the idea of predictive process monitoring is that you have a running case and you want to know the future state of this case. Let's say you want to know what is the next activity, when is going to happen the next activity, how long will be the case, right? Or you want to know the outcome of the process, if the process is gonna be successful or not. With this information, it's possible to make intervention in the process and change the direction of the process. That's the idea. Of course, that has a cost, but if you know with enough time, probably is better for your process performance. So in general terms, this is what is intended to do in predictive process monitoring. In this session, we will focus in the outcome of the process, but it's pretty similar to the other one, so probably the next session will be faster. In general terms, the workflow of this code that we will see is that you have two phases. One offline phase. In that online phase, the idea is to train these models, these machine learning models that are able to predict the future. You take an event log, you extract the information from the event log. This information are usually prefixes of execution. Then you divide this information in buckets, in small groups. And with these buckets, you start to train your classifiers, and then you can classify. But this is like the online mode. The offline mode. This is like the training. In the real life, then once you have this model trained, the idea is that you have a running case. You have to determine at which bucket belongs this running trace, and you can start to classify this running case. So you can start to make the intervention in real life. So, but we will focus in the offline, of course, because we are just in the training part. We are not executing a real process right now. So, considering this, we will start with the first phase, the extract and the filter prefixes. This is the first stage, but actually, before to start, we have a previous one, a previous phase, because we don't know which is a deviant case, for example, right? In the code that I showed you before, the code that is located in the Irene's repository and in my adaptation in GitHub. Let me see. In here, you will find this structure of the code. You have the bucketers, you have the transformers, you have the experiments and pre-processing. So let's see the pre-processing, because every event log has a different definition about what is a successful or what is a failure in the process outcome. So for example, in the case of the sepsis case, you need to pre-process the event log, and according to some rules, define if the process is deviant or is a regular case, right? So in this case, for example, we are taking several measures. We are extracting timestamps, and this is like a basic pre-processing. We already saw that. We are removing incomplete cases because, of course, for training a classifier or for training a model, you didn't need to remove these cases that are not finished. You need to work over the history. And you need to add, okay, we have a question. Which one?
Yeah, I think the links that you posted, the outcome prediction framework and then the adaption are with the same name. Or should I only download the adaption, like the?
Yeah, download the adaption. The adaption. Yeah,
Okay,
it's the
not the
same.
original.
Yeah, yeah. The second one.
Yeah, okay, gotcha. And that's all I have to download there.
Mm-hmm.
Okay, thanks.
Okay. So as I was explaining to you, some basic pre-processing is removing complete cases. Here as well, we are extracting some features that are related with the timestamps. For example, the time since midnight, the month in which the event was executed, the weekday, the hour. This is like contextual information. It's been extracted and added to the event log. And then we have some intercase features. Actually, here is just the number of open cases. We are checking if there is like missing information, missing values, some missing values. And then we are, well, here is like if there is like some infrequent factors, and we are starting to labeling the cases. According to this rule, if this activity exists or not, we are then like classifying of is deviant or not. But here we have a different criteria, and here we have a different criteria, and that is going to happen with every event log. Every event log has their own rules for classifying the instances. So this is like a pre-processing. This is not included inside of the framework. It's something that if you have a new event log, you have to like perform, but it's different in each case. So it's not generalizable. But the extracting and filtering of the prefixes is more generalizable. So let's say what is going to happen in the code. So in the beginning, we will split the code in train and test, basically, with like a rate of 80, 20%. Once we split this train and test, what we are gonna do is split the train in small chunks. These chunks are not the same that the buckets. Is that what is happening is that probably we have a lot of data. So for like managing this big volume of data, we want to split the train information. So this is going to happen in the code really fast, so I'm going to explain it before in here. Once we have the code split in train and test, well, something that we have to consider in here is that we are performing temporal splitting, and this is something that sometimes is not usual in machine learning, and because we are splitting according to a specific moment of time for validate of our approach. So we will define one point in time, and after that point, everything will be considered like the future of the process, and we will be like training our approach with all the past of the process. And that cases that are like splitted in the middle will be removed. This is like strong. We will remove all the cases that are incomplete after this splitting, right? Once we execute this part, then we will move to the extraction of the prefixes of the traces and basic filtering. What is a prefix is, let's say we have this trace. Here we are just gonna show the labels, but we have all the attributes as well. So let's say we have this trace. So from this trace, I can execute every step of execution in time, and we can like aggregate this execution. So this increments in the execution is considered like a prefix, a new prefix. So this is the first step. We want to extract all the prefixes for knowing what is going to happen in the execution of the case, and give that information to the classifier. So in that way, the classifier can start to understand how is the behavior, how is the distribution of the data in the real life. And then of course, like this case was labeled as deviant, all the prefixes are labeled as deviant as well, right? One filter that is applied in this approach is this gap. The gap is that as we are extracting a very long number of prefixes, because it's in each time we are extracting one prefix, we can just skip few of them. So if I said I will use a gap of 2, I will take just the first prefix and the number 4 and then the number 7. So I'm skipping 2 middle. Why? Because sometimes it's not necessary. It's a lot of redundant information. The other filter that is applied in the code is about the performance of the process, because sometimes we have some outliers in the code, in the event log, so we don't want that information. So the most simple filter that we can apply is just remove the outliers, those cases that probably have a case length like really, really long, that is general applied. So in the code, now let's go to the code. This is a lot of concept by the moment. In the code, we have our handout. And here, the first execution, we will import the libraries. Just simple. Now I'm loading the event log. As you can see here, we have 40 columns of data, which is quite a lot. And we have this column with the labels. So all the cases are labeled as regular or deviant. In here, I'm performing one transformation of the timestamps to be recognized as timestamps per se, not strings. And we have here our event log with the labels. So here we have some case attributes, we have some data attributes, we have event attributes as well. So it's a mix of everything, it's the whole information. So the first step was splitting the event log 80-20. We are defining the values in here and the number of splits. This is the number of chunks that we will use for reduce the volume of data. It's just a parameter in the code. Here we are determining the minimum and maximum size of the prefix lengths. This is necessary because not all the prefixes, not all the traces have the same length, and we want to take the maximum as the maximum size of the data frame that we will generate. This is a regular. Here we start with the splitting of the event log. So the first thing is just sort by time, define a moment in time according to the ratio that we defined, 80-20, and then start to divide and remove the cases that are in the middle, that are like in the middle of the two splits, the incomplete ones. And after that, if you see in here, we had how many cases before? Here we have 3000 in the first, in the train, and in the test we have 800 cases from the total. This is for sure more or less than the total number that we had at in the beginning. Let's see, log types, log. So in the beginning we had 3,858, And after the splitting, we have 3015 in one side and 800 in the other one. If we have like really long cases, it's probably that we will like remove more cases because they were in the middle. So from now we will focus in the train set, and then we will just use this test for validate the knowledge of the classifiers. So this was just the splitting by time, and now the extracting of the prefixes. So what we are doing in here in the first method is just extract all the splits. We are stratifying. We are creating a generator in here, and then we will define the ratio between the deviant and the regular cases. What we want to do is like a split in two chunks. First, the data, but we want to preserve the ratio of deviant and regular cases in both chunks. And we want then to split for having like more or less the same quantity of information in all the chunks that we will create. And here, if you see when we are creating the prefixes, these prefixes is basically iterate over the trace and start to create these subsequences. We have this parameter, the gap. Here we are considering all the cases. We are not like jumping between cases. So this is the first set of methods, and with this one we are splitting into chunks everything. So we have our two chunks because we define this as a parameter, and then we have this information. In the first chunk we have like 13,000 prefixes generated from these 3,000 traces, and here we have like 11,000 prefixes from the other half. So in total we create like 24,000 prefixes. How does it looks right now? I'm checking the number of cases. Here I'm checking how long are the cases in each one of the chunks, because it can be like different. And now I'm checking the cases that are contained in the first chunk, just because I want to consider this. How does it looks is something like this. So in the first chunk we have all the prefixes, and let me execute this as well. How this look? I just took 4 of the cases just for checking how are they building, and it's something like this. These 4 cases, if you see, they are like ordered by length, by the number of events, and we are watching that this is like a pyramidal structure, so they are increasing, but all of them belongs to these cases. So that's the first step. I would like to know if you have some questions about this part of the extracting.
So right now we didn't use those libraries we downloaded.
No, right now, no. This is I extract this and I'm calling the libraries from the notebook, but we will check right now where they are located in the code that you download. Right?
Okay.
So let me open Spider, because of course the framework has like 2 parts that you need to consider, but is depending on the application that you are doing. This is like the general concept. Let me continue maybe with this part, and at the end I will show you in the repository where is the code located and how you can like start to find these functions in there, because they are not like straightforward like in here. So this was the first part, the extract and filter of prefixes. The next step is divide these prefixes into buckets. But for doing that, we have like different methods of doing it. We have like, we have for example, just not splitting them, just use all the prefixes, and that will be like having a single bucket, and we will use all these prefixes to train the machine learning algorithm. This is like the baseline. This is, for sure, this is expected that have like a lower performance. The next option that we have is like divide or split the prefixes according the length of the trace of the prefix. So in that case, we will have buckets with prefixes with size 1 and 2, for example, prefixes with size 3, or prefixes with size 7, let's say, is according to the length of the prefix. So we are not considering there if they are like deviant or not. We are just considering the size of the prefix. The other option that we have is doing it based on the state, on the last state of execution. For this kind of bucketing, we need the structure of the process, because each activity or each decision point can be considered as an state, a transition in the direct following graph. So according to the last state, we can also regroup we can also create groups of traces. That means that not all the traces in the buckets will have the same length, but all of them they will finish in the same state, right? So probably you have a trace, a prefix of size 7 that finish in the third activity, and you have one with 3 activities because it was straightforward and just finishing that one, avoiding loops and everything. It's just based in the last state. The other option that we have is like using a machine learning algorithm as well. In this case, a non-supervised one, for creating clusters. And for creating these clusters, the idea is to use the same information of the event and use one algorithm, for example, a k-means. So you can say, I want 3 groups, and this machine learning this algorithm is going to start to learn by the attributes of the event, and he will try to create groups. What is the criteria that is using? Probably depends on the algorithm that you are using. It's a different criteria, and you are not controlling the groups. So it's self-generated in this case. And what can happen, of course, in all of this, that probably you will have buckets in which the ratio of deviant or not deviant cases or regular cases will be really, really different. So the idea is that when you split these buckets, is that at the end you will merge all the results, right? So for avoiding errors or imbalances. There is another option, but I think this last one was removed from the framework from the last versions, probably because it's not like straightforward to understand. In the previous ones, all the buckets are like not overlapping, so you don't have traces that belong to more than one bucket. But in this last one, KNN, you can have overlapping buckets, and so you have traces that are belonging to 2 different buckets, and there are algorithms, there are like classifiers that are classifying these trays in different ways because they are learning in a different way from different distributions. So in that cases, for example, in these trays, just the average of the classification is taken for classify the outcome or for predict the outcome. So again, in the code, how is happening this? So you have this bucket factory. You need to define in the arguments which will be the encoding method, especially when you are using, for example, the clustering method. And you can use the same, these encoding methods are the same that we will see later for encoding the traces. But you need to define an encoding method in here. It can be the last state or some statistics, but we will see these encoding methods later. Then what we are doing is selecting the, we didn't execute this cell. Then we are selecting the method of bucketing, of create the buckets. I think here the only thing that we have to be worried about, if we select a cluster, for example, we need to define the number of clusters that we want to create. This is related with this method with the k-means. So you need to define the number k. Okay, once we execute this, how is the assignment of the buckets? I said I want 3 clusters, and the algorithm just split them in this way. In the train set, then we have 800, 280, and 270. If I change the number of clusters, let's say 5, I will have for sure a different assignment. How it's doing is independent. In the case of prefix, for example, let's change the method. We will have, of course, 24 because 24 is the maximum size of the prefixes we have. Yeah. In the case of a state, say this is the last state. Let's try again. We have just 12 buckets. So each of them has really different characteristics. And the single one, well, is all the information. I think doesn't deserve to try. Let's keep with the cluster and just 3 for the demo in here. Okay, so we will have like 3 buckets, just 3 buckets, and we expect that these 3 buckets will be like enough for our classificator. And now the next steps will be like split all the buckets and start to train the classificators. But before to train the classificators, on each bucket we need to encode the information in there. So I'm not going to execute all the buckets. I will just pick one. I will pick the bucket number 2. So this is the small one, just because of matter of time. But in the framework, all the buckets are executed. So you are creating a lot of classifiers, one per each bucket. Yeah. So here I'm extracting the information and just checking the cases that are contained in these buckets. So the next step is the encoding. So we extract all the information, we create the prefixes and split the prefixes into buckets. That's basically what is done there. The encoding. For encoding, we have as well different methods of encode. Why we need to encode? Because we need to give the information, the prefixes information to the machine learning algorithms in a way that the algorithm can understand the information, and is basically numbers. The machine learning algorithms doesn't understand about text per se. So we cannot use the labels as something that can be used for training the algorithms. As well, we have another limitation, and is that we need to use the same size on each one of the prefixes for give the information to the classifier. Otherwise, he won't be able to understand the changes, and he'll just use this feature vector for start to learn. So we have several methods for doing this, for doing the encoding. For all these case attributes, the case attributes, not these attributes, not the events attributes and the ones that are changing all the time. These case attributes will be encoded using the so-called in here static encoding. That is basically use one hot encoding for the categorical attributes and just the plain values, the values as they are for the continuous features. I don't know if you are like used to the concept of one hot encoding, but the idea is that if you have a feature, let's say in this case the color, and you have some categories for this attribute, you will split or you will create new features that for each one of the categories, and you will mark with 1 or 0. Well, basically you will mark with 1 the category for this observation. So if you see here, we have 3 categories, red, yellow, and green. So for the red, we will mark 1 in the case of these 2 observations, and yellow in the case of this, and green in the case of this, and the other ones will be zeros. So we will have a bunch of zeros and just 1 for indicate 1 category. But it's the way that we can encode these categorical attributes. Of course, there is many other encoding methods for categorical, but this is the one that we are using, is the most simple one, and is suitable in the case that you don't have many categories. If you have many categories, it starts to become like a problem with the dimensionality of the data. But right now, this is like the most basic and enough encoding that we will use. So we have here one example. We have just one trace with three events. We have an activity, we have resources, we have this elapsed time, and we have these 2 case attributes. One is of continuous nature, and the other one is categorical. So the encoding in this case will be the next. We will just preserve the case ID. We will create 2, and we will focus just in the case attributes. So this will be complementary. So we are creating 2 new features for the category 1 and 2 new features for the category, for the CA1, because it's a continuous one, we will just create 1 feature and preserve the value because it's not changing, it's a case attribute. And for the attribute number 2, this categorical one, we are creating 3 new features, and we will mark the corresponding to the category 1, which is the first one. And we are like summarizing all the case attributes in this static encoding in this way. But this is just for the case attributes. So now the thing is how we will encode all the dynamic attributes, all the event attributes. So for doing that, we have again several methods. The last state is one of the methods. So in this case, we won't preserve all the information of the prefix that we are encoding. We are just preserving the information of the last state, of the last event. And again, we are applying the one hot encoding and keeping the information in the case of the continuous attributes. So But now the difference is that we are not focused in the categorical, in the case attributes. We are focused in the event attributes and just focused in the last one. So if you see, for the activity, I create, considering that probably in the activity I have, in the activities, I have just 3 activities, activity 1, 2, and 3. I'm creating 3 new features for each one of the activities and marking the corresponding to the last one, the activity 3. So this will be our one. And in the case of the resource, considering that maybe we have just 2 resources in total, I will preserve the last one. And I will just keep the information of the elapsed time, the last one. So this is one way of encoding, just preserve the last state and say, okay, my classifier doesn't need to learn all the information of the previous attributes. Of course, a lot of information is lost in this kind of encoding. What other option we have? The next encoding is about aggregate the information, right? So in this case, we will take all the information of the prefix, and in the case of the categorical attributes, we will count the frequency of execution of each one of the categories. And in the case of the continuous attributes, we will apply a series of aggregation functions. Like we want to apply the minimum, the maximum, the average, and the sum of the continuous attribute, trying to like summarize all the information of the case, right? So for the activities, for example, in here, we will just count that, okay, this happened once, the activity 2 happens 1, is the same for the activity 3s. In the case of the resources, the resource 1 was executed twice. So we have the number 2 and the resource 2, just 1. The minimum value of the elapsed time was 60, and the maximum 3000, and the average is 1080, and the sum is this. So in this way, we are preserving more information. Of course, we have more features than in the previous encoding, if you see. We are preserving more information, but again, we are losing some important information, like the order of the activities. So we are having like one encoding, but in a very, very like big aggregation way. So for trying to solve these problems with the aggregate encoding, we have the index encoding. What happened with the index encoding is like for each one of the indexes, each one of the events, we will create new features. So if you see the biggest problem that we have, or that we are going to have in here in the case of the index, is that the dimensionality of the event log will increase a lot, because we will have a lot of features that we are creating for each one of the events. So just for these 3 events, for example, we have like 15, 18 attributes, and you need to add the attributes corresponding to the static features. So we will have like a very long list. Again, for the categorical attributes, we will create one hot encoding. We will apply one hot encoding. And for the continuous attributes, we will aggregate. We will apply. No, excuse me. This is not aggregate operations. We will use it as is, because we don't need to aggregate anything. Of course, you can mix as well the encodings, because you can use the aggregation, for example. You can generate this minimum, maximum, average, and adding to the index one, and you can like have more features for giving us information to the classifier. Yeah. So yes, in this case, for the event number 1, as you see here, I'm preserving the information. Event number 2, event number 3, in the case of the continuous attributes, and in the case of the categorical ones, I'm marking for each one of the events, and I'm concatenating them in order. So these are like the encoding methods that we are using. So questions about the encoding? No questions? Okay, so let's check in the code. How is this applied? It's very quick. The idea is to understand how we are doing this. Okay, I'm coding here. I'm just defining as argument which ones will be like our static categories, the static numerical columns, the dynamic categories. So in this case, we have the activity and the resource, and the dynamics number columns that I want to encode. And I will define some methods for all the traces. I will apply the static encoding for the case attributes. So for these attributes defined as static, I will apply the static. And for all of these, I will apply the last aggregation or index encoding, depending as I want, as we want to apply it. Or in this case, for example, is combined. So yes, I will use the index one. Well, maybe I can show you the aggregation one, and then how it changes when we use the index one. With this library, Feature Union from scikit-learn, we can apply this combination of encodings in an automatic way. So we are defining a transformer of the features, and we are encoding. So from these 13,000, no, from here I took the bucket number 2. So from these 278 cases, I'm generating the same number of encodes. And this looks like this way, but this is the information in the bucket. So now I will, this is more easily to check in a CSV file. So let me come here. I should generate this file in Excel, just for checking. So this is the result of encoding this bucket, right? So we have, for example, this is an attribute. We have a lot of zeros, and for sure here we'll have like one. This is the first category of the first attribute. So if you see, we have a lot of features and new features that we create. These for sure, I think these are the values of the dynamic attributes. And at the end, we have all the information in here. This is encoded, and this is the way that we are going to give the information to the classifier to learn. Let's change the method.
What is the dynamic attribute? What?
The dynamic attribute is let's say is like an attribute, and it's an attribute that is changing in every step. Yeah, like for example, the activity, the label activity can change in every step, so it's dynamic. Every event attribute is dynamic, let's say, and every case attribute is static because it's not going to change during the whole execution, right?
Okay.
Okay, so yeah, this is aggregation. If you see, we have these values. We have how many categories having here? we have 192, right? New features for training. And let's change the encoding method for index. This is the same. And it's because I opened this. This was 192. Okay, let's open this. For sure, the index one is the biggest one we have. Again, we have the static, and here we have like the information of the dynamic attributes. You see, is different because for each one of the observations, we are creating new features. So at the end, we have like 582 features for training the classifier in this case. So the way as we encode information will affect a lot the classifiers and also the size of the buckets. And this is the encoding part. And the last part is, okay, we have encoded our bucket. Now let's classify, let's train the classifier. And which classifiers can we use under this framework? We can use random forest classifier. This is decision trees, basically, but of course, a bunch of decision trees for classification. We have XGBoost. XGBoost is a framework for classifying that is using as well decision trees, but some very weak decision trees. And the framework what it's doing is mixing these decision trees for getting a better classifying. So, and of course it has a lot of features for make better the performance of the whole approach. So this is a framework, a complete framework, and can be applied for classification and also for regression task for predicting, not categories, is for predicting values. This will be used as well in the prediction of the next event and for the prediction of the remaining time. Logistic regression is the most simple classifier, I think. It's just you need to define a logistic function for dividing two categories. And supporting vector machines is like a classifier that is creating a plane for splitting the data in different dimensionalities, let's say. But the idea is to find a plane that can split the data in the best way. Here in this image is just 3D, but usually the supporting vector machines work at higher levels of dimensionalities. So we can use these 4 classifiers in this approach. Just for showing you, that's like the last step. If you see, I think the 80% of the whole process is pre-processing. I'm gonna use here just a random forest classifier and encode information and pass that information to the model. I'm fitting the information then, and then I can start to predict actually. Execute twice. So this is just the whole training, and now we can predict. How looks the prediction? Looks like this. What I did in here was, okay, I trained the classifier, and now I'm saying to the classifier, okay, make the same number of predictions that was in the, not in the training, the same number of prediction that is in the testing split, and the testing split that corresponds to this bucket, because every bucket has a testing split that is belonging to. And now I can compare, and using the regular classification measures, I can define if the classifier was good or was not good enough. In this case, it was not the best classifier. Let's say it was just 0.49. It's almost like a random classifier using this measure. The measure that we are using is the forgot the name of this. AOC is in the area under the curve, of course. If you see a good performance has to be over the 0.5 when we compare the true positive rate against the false positive rate. A perfect classifier is the one that is obtaining like 1, is classifying everything perfect and is not failing in any case. But it's really hard. I mean, it's not even hard to this situation occurs. If it occurs, it's because probably your algorithm is being like overtrained or something. It's not natural that it happens, it's overfitting. So you are looking for something like between 80 and 60 can be considered as like a good classifier that can be complemented, but it's not a standard. But of course, if you are having less than 50%, it's because something is happening and you need to change probably the encoding method or add more information or check all the pre-processing of that you were applying. Also, you need to modify the values in the classifier, the hyperparameters, because each one of these techniques have like different hyperparameters to be executed, and that affects how they are learning. But it's very hard to find the values. So for that case, the idea is to use a hyperparameter optimizer to find the right values in the classifiers and use the same encoding information. I want to show you again. This was the results for just one bucket and one execution. I execute this before because, of course, as the framework, as I am going to show you, the framework is using an optimizer for finding the right values for each one of the classifiers and is classifying for each one of the buckets. All that process take a lot of time. So for doing online is almost impossible. Here I execute this information that we are watching here is just the information of two classifiers, random forest and XGBoost, and how are the scores in classification after each one of the optimization phases. And the results, the final results are these ones, for example. And we are like watching the results according to the prefix size. So we have like very good classification in the case, for example, of having 15 events. We can say that we can, with random forest, we can classify correctly like the 70% of the cases, which is quite good. And in the case of XGBoost, we can do it like over the 60%. But when the traces are like becoming longer, the performance of the classifier decreases a lot. So for the long traces, the classification is not as good as we expect. Of course, that in this case, I was using the clustering method and the index method. So I was using a lot of information, but you have to, for find the best classification, you have to try all the bucketing methods and all the indexing methods, all the encoding methods and all the possible classifiers. So it's a lot of possibilities that you have for finding good classifiers. So now in the code, let's see in the code where you can find all this information, because it's not like as straightforward as was in the notebook. But for explaining the concept, I think is enough. Do you have any question by the moment? No questions, okay. So I will go here. So in the one you found, okay, this is the structure of the repository. So you have the bucketers in here, all the cluster one, no bucketer. This is the same single bucket, prefix length, and state-based bucketer. You can like use in your own applications if you want. You have the transformers. These are like the encoding, the encoding methods. You have the aggregate, the index, last state. Here is a new one. This was not in the previous version of the approach. Is the previous state transformer and the static transformer. But most of these transformers were explained how they look in code. Let's see. Let's start for the state-based. So you can see how they are in order to simply. Oh, we can. Let's see. Maybe one more. This bucketer, for example, is just taking the event log and the case ID column, and is grouping by the case ID and measuring the size. So it's measuring the size of each case ID and creating groups according to that, and is returning to the groups according to the size. So it's simple. This is the fit function that we were calling. And this is the fitting, and the prediction is executing the whole assignment and returning the values is what is happening here. And fit and predict is doing the two actions. So actually this is how is defined a bucketing method. Let's look, for example, the encoding method, the index method. So you are at the beginning of the class, you are defining all the attributes that will be used in the fitting and in the transforming. That is what we are executing. We are grouping by case ID, and then we are defining the max number of events. If we remember, the index base is encoding each one of the events that are being executed. So we are grouping, and we are transforming each one of the events in one hot encoding, and here in one hot encoding, and using the values as they are for the continuous values. And then we are returning a data frame, like a new generated data frame, taking as an input the original data frame. So is not really complicated to develop one of these encoders. And once you like define all the structure, you can reuse them in the framework. These are the transformers and the bucketers. Also, we have the preprocessing I showed you before, and then we have this folder with experiments. In the experiments, we will focus on two of them. The first phase is the optimization phase. Basically, is this file optimize parameters. And here we are executing the same that I was explaining in just one column, but we are starting from here. The idea is that you receive the parameters that you will use from maybe another main class that is not proportionated in the framework, but you need to define the number of iterations, the bucketing method that you will use, the encoding for classification, and the classification method that you will use. These are like the parameters that you are receiving as console parameters. We start to execute all the encoding. Well, here I'm creating some results. reading the data. We are defining the columns in the data set, determining the minimum and the maximum length for each trace that was as well in the notebook, splitting the data set in training and testing, preparing the chunks that was executed as well in the notebooks, and then some values for the optimization. For each classifier, we have different values that can be modified. For example, for the random forest, you need to know the maximum number of features that will be considered before to create a new branch in the decision trees. For XGBoost, you have learning rates, for example, you have subsampling, you have maximum depth in each classifier, because this is as well like a kind of random forest. So you want to create a small decision trees, but you need to define the maximum depth. The call sample, the sampling that you are taking for creating a tree, and you can define here a lot of parameters and the values that you want to explore in each one of the hyperparameters of each one of the classification methods. So if you want to create or adding a new classification method, let's say CatBoost, you need to add in this method, in this part of the code, you need to add it and add all the parameters that you want to explore for that classificator. Here we have logistic regression and the values corresponding. So here we are defining the search space that will be used in the optimization phase. And then you start to optimize the parameters. So we are calling this method that is defined in here. And here what we are doing is iterating over the chunks that we create at the beginning, and for each one of the chunks we are creating the buckets, and then we will start to iterate over the buckets and extracting the features, extracting the traces belonging to that each one of the buckets, and training each one of the classifiers. This is what is happening here. You are extracting all the information for all the chunks, buckets, and classifying them, and training your methods. This is this is all the training part in here. And then at the end, what you are doing is predicting according to the test partition. You are executing predictions, and then you are measuring the performance of the classifier. Once you measure this performance, you are calculating a so-called score, and this will be used as a loss function in the optimization phase. So after executing this a number of times, probably it depends on the number of iterations that you defined. After executing this, let's say 15 times, you will get like you will get a set of values that are like the best values for this classification method, bucketing, and everything, for this classification method, excuse me. So when you have this information, you can start to predict, let's say, use the information. And for use these values, you go to this file experiments. So we have optimized parameters, and then we have the other one is called experiments. And in experiments, you need to define as well the same values that for the data set, of course, which will be the parameters directory. So it's the directory for taking the parameters that you get in the optimization phase. Yeah, the results directory, the bucketing method, the classification encoding, classification method, All this information is the same. Here you can define the gap and the number of iterations. This is how many experiments do you want to execute for minimize like the random variation in the results. And the same pipeline is executed, but taking just the value of the parameters that you find in the optimization phase. So you need to execute both phases. First, the optimization for getting the best values for the classifiers, and then the experiments for execute these values that you found. And yeah, at the end you get the results, and the results are like the same structure that you saw in the notebook. So what I did for explaining was taking the part of the information that was in this framework and just organize it in a single pipeline, because it's a little bit more easily to show you the coding that way. But it's the same, so you won't find like problems with the code, I hope so. Probably it's something that will be challenging for you is that, let's see, is that in here you have this structure of bucketers, transformers outside, but when you are executing the optimizer and the experiment, you are calling the libraries, but they are outside of this folder. So something that you can do is simply move the bucketers and the transformers inside the experiment, so you won't have problems like importing the libraries, let's say. And for changing the values, you as well can do something like this in the optimization. Is just modify the parameters. You can comment here. If you don't want to receive them by as an argument by console, you can define the values directly, like in this case, for example, what I did here. And that's all. I hope you could play with this code. So, questions? Do you have questions about how to manipulate the code? Could you install everything?
Yeah, everything is installed, but we should. Can you show again what should we copy to where? I didn't catch it.
Okay. Okay, let's. Oof, it's a lot. Yeah, so let's start from probably from here, from for example, how you get the event log information. This is predefined in the code. I think I didn't show this. In the framework, this is defined in here in dataset configuration and dataset manager. Dataset configuration have the information of the routing and each one of the names of the columns that are being mapped. For example, which is the case ID column, which is the activity column for this specific event log. The resource column, timestamp, label column, the name, and which are the categories. So this is something, if you are like adding a new event log, you have to define this, and then you can call it, you are assigning a name for this event log, and you can call it directly as I did in here, as I did in the optimization phase. You can call it as a reference in here. That's for importing the code in the framework. The second step, for example, I took the code, when I split the train and test splitting 80-20%, I get this information from here, from the optimization phase. You come at the end, just starting here. Here is mapping the event log, and then you start in here, splitting the training and testing. So it was taken from here, right? And the ratio and these parameters. Of course, we are calling functions that are defined in other parts. For example, dataset manager here has all the methods for splitting the data in different ways. Time strict for discarding events, split values. Generate the prefix data is located in the dataset manager as well. Getting the indexes. Here is a lot of helper functions for managing the information, for getting the information from the datasets. So yeah, I'm calling these functions are located basically in the dataset manager, including the splitting data. Extract and filter prefixes is the next step in the optimization. For example, we are here splitting in chunks, and we are calling this extraction for each one of the chunks and creating the prefixes data, right? But these methods are located in dataset manager. The ratio of classes and the prefixes generation is as well located in the dataset manager. Then how to divide the prefixes into buckets is mainly in the bucket factory. And these methods are called in this pipeline here. Well, here this part is just defined for each one of the models. So inside of each one of the buckets, you are starting to perform these activities. Let's see, this is getting the information for each one of the buckets and encoding the buckets. So it's the beginning of here. For each one of the chunks, you are getting the bucketer, fitting and predicting. So you are like dividing the information in the buckets. Here is all the information, right? And extracting the information in here. The next part is, well, this is just assigning. I was exploring here, so this is not necessary. The encoding part. So for each one of the buckets is in here. Actually, is just get relevant data. Let's see where is the encoding part. Get indexes, get relevant data, get label. It's in here in the pipeline. You are defining a feature combiner in here. It's super fast because you are just defining which will be the method for encoding and for each one of the methods. And with this function pipeline, you can encode and execute the classifier. Okay, here is one precision that was not made previously. For the supporting vector machines and the logistic regression, you need, once you encode the data, you need to scale all the data, because these classifiers are like sensitive to the scale of the data. And okay, that's the encoding part. And finally is just execute the classifier, train the classifier, but in the code of the framework, everything is done just in here. Here in this part we are training, and here we are predicting just with one line, because of course we are using this is a framework over another framework, and the main framework was scikit-learn, and these functions come from scikit-learn, and they are able to execute the whole pipeline in once. So I just use here step by step for explaining, and then is the measurement of the accuracy of the model. It is the last part is done here, and the returning of the score in here. So yeah, I think this is how it's related, the code in the notebook with the code in the framework that we were using, right? So any other question? No more questions? Okay. Okay. Yes, today was a demo. I hope that this information can be useful for you, because it's part of the homework that you need to work for in the next week. So, and in the next week we will start with the next topic, which is remaining time prediction. It's just a minor addition to this framework, a very, very minimal modification, and we will add a new kind of technique, in this case, LSTM model for predicting the remaining time. And after that, maybe we can check the problems that you are having with the code in the repositories. So this is all for this class by the moment, and if you have any question, I will be pending of receiving the questions.
Manuel,
Yeah.
could you please share the recording of the session after that? Like after the practice session? It's going to be shared.
Share do you want I share what? Sorry, I couldn't listen to
I
you.
think you are recording the
Yeah.
practice session, right?
Yeah.
Yeah, please, because I think it would help for like debugging the error or something. Like
Yeah, for sure.
the error better.
Yeah, for sure. That was the idea of recording. I will share the video. Yeah, thank you.
Okay, thanks.
Okay. Okay, guys. So I hope you have a nice rest of the week, and see you later. Bye.